G was a compact Lie group. Then we looked at the Lie algebra G, and we looked at subalgebras which are maximal abelian, which always exists. And then the property was that T is unique up to conjugacy, so in other words, up to at. I can take one into another with the adjoint representation. And the other important property was that if X lies in G, I can conjugate it into this subspace. Lies inside the maximal abelian subspace. So that's what we proved last time. I forget if we proved something else or not. Just quickly look. I think that's it. Okay, so then I mentioned one can look at what we call the adjoint orbits. Inside the Lie algebra, or what sometimes also is important inside the doutorado2012 algebra. Well, let me talk first about the Lie algebra G itself here, what these orbits look like. So we said, well, you take X in any take vector in the Lie algebra, and then you define an orbit. So let me give this a name. Let me call it O, which is the conjugate all the elements times X. So this is a submanifold inside the Lie algebra, compact submanifold. Of course, it's homogeneous by definition, right? I have this group acting on it. By definition, this orbit is the group G divided by the stabilizer, right? So divided by the subgroup or those elements G such that at G fixes X. So that's a stabilizer. And of course, so by this result here, I can assume that my element X lies in the maximal abelian subalgebra, because I can write every adjoint orbit in this form. Because every orbit, this means that every orbit meets the maximal abelian subalgebra. So you might as well take your vector inside the maximal abelian subalgebra and then take the orbit. So then this has a lot of geometry, this adjoint orbit, and the one I want to explain right now is that O is a symplectic manifold in a natural way. It's even more than that, it's a Kähler manifold, but that's a symplectic manifold I can explain very easily now. So it's a submanifold of this Euclidean vector space, right? I have to define a symplectic form on it. So I want to first understand what's the tangent space of this submanifold. Right? So let's say pick a point P in the orbit. So I can write P as at G of X. And then what's the tangent space of P at the orbit? Well, I take a curve in the tangent to O starting at the point P. Right? So I can do it as follows. Times G applied to X. Right? So if you want to, let's maybe first go inside here, right? So X dx times G, that's a curve starting at G, and the tangent vector is X. I can write every vector like this here, where X is some vector in the Lie algebra. Right? For each vector in the Lie algebra, I get such a vector. Tangent space is spanned by that. So I differentiate that, and as we know, that's a Lie bracket. Right? So let's write it as follows. Right, I can bring this outside. I can say, well, that's at xtx times at g times x. Now differentiate this part here with respect to t, and I get a Lie bracket. So it's a Lie bracket of x with, sorry, because I shouldn't take the same x, because my vector x is fixed. I'm looking at the vector at the orbit, so let's give this a different name, right? So the z should go in here, because that's my tangent vector. Whereas this is the vector through which I look at the orbit, right? So Lie bracket of x with this vector here. Z. Lie bracket of z. And that's what differentiating this gives me with the vector there, with at g of x. So set up all that where z lies in the Lie algebra. Another way of saying that is it's the image of at g of x, of at g of x. All right, so here's at gx, that's my fixed vector. At of that is an anamorphism. I apply this to any z. So the image of at of this here gives me this set, this vector space. Right. So tangent space at this would be at the point gz, gx of O is the image of at gx. Right. On this vector space, I want now define a symplectic form. Of course, I can, for simplicity, let's do this as follows. Right now, instead of looking at x inside the maximum torus, I can take any vector in G, and then I look at the tangent space at x of the orbit. So by changing from the point gx to x, if you want to, I should give a different name maybe, let's call it y, right? Then I get the same tangent space, it's just the orbit. So think of this y as at gx. It's just a different way of describing the same tangent space. So this is now the image of at y. That's a little bit simpler way of looking at it. So on this image here, I have to define a form. So in the image, things are described by taking Lie brackets. Y with R and Y with S, say, right? For some R, S in the Lie algebra. Right, this is every tangent vector can be written in this form. Right? And I have to define that symplectic form. And there's a natural way to do that. Namely, I take the inner product of y with a Lie bracket between R and S. Say where this is a bi-invariant metric. On the Lie algebra G. Right. So here I'm using the fact that my Lie group is compact. So it's a very natural way. Right? The bracket, the symplectic form is just given by the Lie bracket. Notice that if I switch these two around here, that switches these around, so it's symmetric. Right. So exercise is that omega to the n is non-zero, where the dimension of the orbit is 2n. So in particular, it says that the orbit is even dimensional, right? And then the top power of this is non-zero, and also that d omega is equal to 0. So that gives me a symplectic form of this vector space, right? This, if I do this here, so compute d omega should reduce to what property? You can kind of guess what this should involve. you can guess, why should this be 0? You can kind of guess what the reason behind it is that should be 0 in the computation. I'm not going to do it. But what do you expect?
Some sense the closeness is equivalent with the Jacobi.
Exactly. Should have to do with Jacobi identity. Right? If you crank it out with the computation, it should be in the Jacobi identity. Maybe I assign this as an exercise. And here you have to prove non-degeneracy, for example. Okay, so that is true. So they're important examples because they're natural examples of symplectic manifolds, homogeneous symplectic manifolds. Right? The group G acts transitively on it. And then the other remark I make is that, because here, so the assumption was that G is a compact Lie group. Right? Because the compact Lie group had a bi-invariant metric, and here I took the inner product with a bi-invariant metric. And you probably use the bi-invariance to prove one of these things. Anyway, so I can do this for any Lie group if I let at G act on the dual instead of on the Lie algebra. So in the following sense, right, at G of some functional must be another functional, so I apply it to some vector x. What should it be? Well, f of at gx. Of course, right? It's the only natural thing to do. So there's a natural action of this on the dual of the Lie algebra. Of course, in our situation, it's not really any different because we can use the inner product to define an isomorphism of from G star to G. And since at G acts by isometries on inner product, this is an equivariant isomorphism. So the action here and the action here, if I do this, is the same thing. Right? So for compact Lie groups, there's no advantage of looking at the Lie algebra. But if I look at it this way, I don't need any inner product at all, because then I can regard this here, so on G star. I can regard this as y, the point is now an element in G star. It's a functional, and I simply apply this to the Lie bracket. Right. So therefore, I don't need an inner product here. And now the same computation is true. This is symplectic form, d omega is equal to 0. So every co-adjoint orbit is a symplectic manifold. Right? And that's true for every Lie algebra. It has nothing to do with compactness. More is true that this also has a complex structure, and that's not quite easier to write down. So I claim O as a complex structure, J such that omega Jx, x is positive. So I can think of this here as an inner product of x, x. Because it's positive. J being complex structure means it's symmetric. So this makes this orbit into a Kähler manifold. So I'm not going to talk about this right now, so I have to know what a Kähler manifold is. Like if I have a symplectic form and a complex structure, I can define what it means to be Kähler, and these are Kähler manifolds. To define the complex structure, one uses root spaces. So I think you asked me this question, right? What's a complex structure? Symplectic form is very easy to write down, right? The most natural thing that you could possibly think of. For this complex structure, it's a little more difficult, and this we're going to be able to do after we talk about roots and root spaces. Then one can write down a formula. Without that, I'm not quite sure how to do that. Then, in fact, one can describe the set of all complex structures which are invariant under the group action. Okay, so this just wanted to mention about adjoint orbits, co-adjoint orbits. That's a very important subjects. I mean, a very important example in many different subjects, these co-adjoint orbits. And we'll be able to understand them a little bit better next. So what I want to do now is, here we saw that at G of x intersects the maximum torus non-trivially, right, for any x in the Lie algebra. If you want to, I can just think of this as the orbit, because the x is not important, right? Only the set is important. Think of this as the orbit. Every orbit dissects the maximum torus, and the question is how many times? So what's the set? Right? What's the orbit intersect T exactly look like? I claim it's finite, and one can describe exactly what it looks like. But this one introduces a Weil group, what's called a Weil group. Of the group G with respect to the maximum torus. So with respect to some choice of the maximum torus. T, which is the image of the maximal B in subalgebra inside G. So here's my maximal B in subalgebra. Look at the image inside G. And remember in the proof of this theorem, last time we proved that T is compact. And because T is abelian, there's also abelian, compact and abelian. So indeed, this torus is a product, is a usual torus, product of circuits. Right. And the dimension of this torus, or the dimension of T, we call the rank of the Lie algebra, or the rank of the Lie group. It doesn't matter. So now I define the following. Maybe I look at W, which is normalizer of the torus, divided by the torus, or divided by the centralizer of the torus, if you want to. So here, inside the Lie group G, so sometimes I use this notation for normalizer and centralizer. Sometimes I specify in what group do I mean this. So normalizer of T is just well, set of all elements that normalize it, right? So that requires natural action, which is the adjoint. Well, sorry, we're on the group level here, so this is in the group, so I might as well conjugate then, such that G inverse is contained in T. And the centralizer of G should be what? So what's the centralizer of an object, if you want to? Conjugation is the identity, right? So if you want to G inverse equal to T for all T and T. Right? Something that preserves it, but something that is identity on it. Right? So this kind of quotient often is very important in all kinds of different structures, normalizer divided by centralizer. For the centralizer here, in fact, the centralizer is normal in the normalizer. It's a normal subgroup. Right, conjugate with something that preserves the Lie algebra. So it's good to if H lies in the normalizer. Take a conjugation. Where's the centralizer? So HT, H inverse. That will be conjugation. What do I have to show? I have to show it lies again in the centralizer. So I show that this element has to be identity. So applied to an element T in the maximal torus. So let's see. So what does that mean? It means that I conjugate, right? HG, H inverse times T times the inverse. That's H, G inverse, H inverse. And of course, that's now H, G, H inverse TH times G inverse H inverse. This identity, that's the definition of the centralizer. Right? that's HG T, G inverse, H inverse. Let's see. I want to show it's normal. Because of course that means I have to choose something in the centralizer. That means I should choose G in the centralizer. And I want to show that this again lies in the centralizer. So I apply to T. H lies on normalizer, so this is not quite true, right? Okay, so let's erase this. I claim that's okay. Because what I want to show is I want to show that this element lies in the centralizer. Sorry, HG inverse.
The second step is confusing because
This one?
no,
This one?
yes.
Because this means here conjugation, right? What is this action on T here? It was by conjugation.
But you don't want to see conjugation. You want to see that it commutes.
Which means conjugation acts trivially. So I have to show that here now T is a vector. Maybe that's a point in the maximal torus. And I want to show the adjoint of that acts trivially. G is in the centralizer. Okay. Where does this element lie here? H lies in the normalizer. It normalizes T, so this lies in T. Lies in the, in T. That means it commutes with G, right? Because T lies in the centralizer. So this is H inverse, T, H inverse. And that's T. Now they cancel. So on this element T, deep conjugation acts trivially. What's the normal subgroup? But that's a general principle, right? Whenever you define something like this, the centralizer of whatever object is always normal in the normalizer, and therefore the quotient is a group. Right? So this here is really a Lie group. Because, so why is that a Lie group? Well, what can I say about these subgroups? I have a subgroup normalizer of T inside T, and I have the centralizer of G inside T, inside G. What kind of Lie groups are there? What kind of subgroups are they? Why are they Lie subgroups?
The centralizer is clearly closed.
Right. And the normalizer? It's not so closed, right? Normalize this condition here. Notice that if you want to, I can multiply G on the inverse. It's the same thing as saying they're equal. Right? Doesn't matter. And so it's an equation. That's also an equation, so they're compact. So that means that this is closed in here. So it means the quotient is a Lie group. Right. So now you want to study this Lie group. Maybe the first thing I should do is that the centralizer is actually very simple. centralizer of G in T is just T. So it's not any bigger. Certainly T lies in it, right? Everything T commutes with it. T is abelian. The question is, can it be bigger? Claim is no, because T is a maximal torus. So let's see how that goes. So take an element G in the linear G, such that T G inverse is equal to T for all T in the maximal torus. So lies in the centralizer, right? And now just look at the group A generated by G and T. They commute, right? So I can just look at the group generated by those. So this will be a subgroup inside G. I claim it will be also compact. Let's see, why is that? Well, T is certainly compact, right? We also know the maximal torus is compact. It's a group generated by an element in the maximal torus. So what does this look like? So A is on the form G to the n times T for all n in Z. Well, is it closed? It's certainly a subgroup, right? If I take something of this G to the nt, G to the mt, they commute, so it's G to the n plus mt. Because this is what I'm saying here, right? So generated by, in this particular case, because they all commute, it's just elements of this form, right? Why is this compact? So is it closed, right? Or equivalently, does G have finite order? There's some power lie in T, I guess. So some way I can look at this where it's closed, obviously. Do I say this? Yeah, I just say it's close to being compact, clearly. So why is that clear? Certainly abelian. If I show it's closed, it's compact, so I'll have to show that A is closed. So take a sequence of elements, I guess, right? So what does that mean? I take G to the ni ti for some ni and some ti in T. And I can go to infinity, right? That's the problem. Is a group generated by two subgroups always closed? So I can think of A as the product of everything generated by G, where G is fixed. That's certainly a subgroup. Now multiply this with the maximal torus. Because this might be an infinite group. This might be Z. So that's probably not the way to look at this.
Why don't you take the closure?
Yeah, maybe we should just take the closure. So A closed is compact. Certainly, because G is compact. So A closed is compact, particularly it's a Lie subgroup, right? Which means also that A bar has only finitely many components. And let's say A bar 0 will be the energy component. What can I say about the identity component? I claim the identity component should be the maximal torus. Was observe. Closure is abelian, right? It certainly contains a maximal torus, and maximal torus is maximal, so it must be equal to the maximal torus. Okay, so have a group with a abelian group in G with finite many components, identical components of maximal torus. I claim this implies there exists a G in A bar such that the set of all powers of G, so a different one, let's call it G tilde, right? For all n in Z is dense in A bar. So let's think about this, why this should be the case. Let's first think about a maximal torus. Whatever maximal torus, I claim there's an element such that all powers of the element is dense in the maximal torus. How would I do that? How would I construct such an element?
You can take a lecture of purely irrational smoke.
Irrational.
Rational.
Rational?
Irrational.
Irrational, yeah, okay.
Of transcendence degree, the dimension of the torus.
Yep. So when
And
we've,
that should be
we've done this before, so there exists an element in the Lie algebra of T such that, if you want to, the one parameter group is dense in the maximal torus. And then so now I can have choices for T, so I choose T irrational. So now choose T naught, say, irrational. And then let that be the element, right? So let's call it G tilde again. So all these elements, if I take powers of that, it's going to be irrational. It's going to be dense inside this the circle. Inside this dense subgroup, right? And therefore this is the element I want, right? So G tilde to the n is dense in XPX and hence in G, hence in T. So that I can use for a maximal torus. And now I have this group A bar, whose identity group is a maximal torus. We just only finely many components. Right? So I choose something in G bar so that some power lies in T. So there exists an n not such that G to the n not is an element in maximal torus. And I want to choose my I want to choose a G tilde in G times T such that G tilde to the n is dense in A bar. Well, I can modify my G tilde with anything in T and still lie in A bar and just look at a different component if you want to, right? So just modify this with an element which has this kind of property here. Right? So eventually, after I take sufficiently many powers, I'm going to end it in a torus, and then I use this kind of property here. So such an element exists. What does that mean? Say it again?
You can choose such an element in the torus or each copy of the torus. But
Doesn't matter. I mean, this I know that this is some and not, so this lies in T here, right? And then this here specifies a component. Right? This specifies a component, and then this power eventually lies in the maximal torus. And now I choose this element in T here, so that I end up with an element like this inside the maximal torus. So whenever I take an integer multiple and not, I get elements in the maximal torus, and that will be dense in the maximal torus. So what does that mean? Let's see. Let's see. So what do we have here? Is that this is another trick. There exists an element G tilde, so that's that all powers are dense in A. Now I can say, well, there exists a new maximal torus, let's call it S, such that G tilde lies in it. Because we know that every element, given a maximal torus, every element is conjugate to something inside the maximal torus as a consequence of this here. So just choose some maximal torus which contains G tilde. That's going to be different than the other maximal torus. But there certainly exists something like this. And what do I know now? I claim that T commutes with with A bar, certainly, right? By definition. I want to use maximality or the maximum torus S. So I want to say T is contained in S. So T commutes with A bar and hints with S. Hints with G tilde, maybe that's what I should say. Other way around. How about saying like this? This new element G tilde, which was contained in my new maximal torus S, has a property that G tilde commutes with T. A property, G tilde was in A, right? T lies in A, commutes with everything. It's an abelian group. Right? A bar is an abelian group. It's a closure of something abelian. Contains T clearly, so this element G tilde must commute with T. But the powers are also dense in T. Let's see. Actually, this implies S lies in T. Or T lies in S. Which way around does it go? So G tilde lies in S. I can also say that G tilde commutes with S by definition, because S is abelian. Now then T must commute with S by denseness, right? So S commutes with G tilde and hints with all the powers. Right? But the powers generate T. So S commutes with T. Now by maximality of this implies that S is equal to T. Right? Otherwise it would have a bigger maximal torus. And of course G tilde is also contained in S by definition. So that implies that A bar is contained in T also. So S computes with T, G tilde commutes with it. All the powers of G tilde generate T, it's dense in T, so all of A bar lies in T. In fact, by maximality, A bar must be equal to T if you want to. Okay, so I showed that I can modify, so this group here was a set of all powers of G multiplied by the maximal torus. And then I said I'm modifying my element so that all powers are dense in it. And then I show that this new element lies in the maximal torus, so G tilde lies in it, right? Lies in S. But now we show that S is equal to T. So all of A tilde lies in T. A tilde contains A. So A lies in T. So I found some maximal torus which contains A. So it means that A is equal to T. So that shows this. Okay. So what did we want to look? We want to look at the normalizer mod the centralizer. So I can replace the centralizer by T itself. So the double while group is a normalizer of T and G divided by T, which of course is contained in the normalizer. So now I want to prove the following properties of this while group. A, W is finite. B, W acts on T, on the Lie algebra of T. And C, if I look at an adjoint orbit of any vector x intersected with T, well, as I said, I want to see how many times does a T. The claim is that's the same thing as taking the while group orbit of, well, so maybe I should say it this way. Remember that for this adjoint orbit, I can take any x here that's conjugate to it. So you might as well conjugate into the maximal torus first, and then look at the adjoint orbit. Right? So that was the same thing. So now x lies in T here. I look at the adjoint orbit, so that vector in T inside G. Now I want to see how many times it intersect. And I claim it's the orbit of W. So x lies in T. This here claims that it preserves T. Right? So W here goes from T to T in the Lie algebra. And so this here also lies in T. It's an orbit inside T of the vector x in T under this finite group. Right? W is finite. So that means particularly this vector, this set is finite. So every adjoint orbit intersects this maximal abelian subalgebra in finitely many points. Like these finitely many points you can write down once you understand the while group. And that's certainly something that's going to be crucial to understand the while group. So let me prove a little bit of this at least. W is finite. I know the normalizer is compact inside G. So I guess I want to show that T is the identity component of the normalizer. The group is finite. There are only finite many components. So if I can show that, then the while group is finite. I claim that follows from our lemma. Let's see. Let's go again. Look at the Lie algebra, right? I'd like to show this here. So let's convince ourselves they have the same Lie algebra. Right? T is clearly connected. This group is not necessarily connected. In fact, certainly not connected. If I show they have the same Lie algebra, so then that is certainly an identity component of this Lie algebra here. And then by compactness of this here, it has only finite many components. Okay, the same Lie algebra. What's the Lie algebra? Well, that's our maximum B and subalgebra. What's the Lie algebra normalizer? So I think that was one of the exercises. Should be the normalizer inside the Lie algebra, right? What else can it be? So what does it mean to normalize in the Lie algebra? It means it should be the set of all vectors that normalize a maximal torus. Set of all x, sorry, that normalizes. Set of all vectors x, which normalize the maximum B and subalgebra, which is the Lie algebra of my maximal torus. Right. We proved that, or you prove it with the adjoint and the exponential map. Right? So that's a natural kind of way one proves this. So if something normalizes the Lie group, the Lie algebra of that is something that normalizes the Lie algebra. Okay, so I have to show that this Lie algebra is equal to T. So I have to show that if this is true, then it lies in T. So now I do our trick that we already did last time. Choose a y in T such that xty is dense in the maximal torus. Right? You can always do that. It was a trick on Monday. Proves several things. So now let's take this vector x, which normalizes the maximal torus. Particular x comma y is contained in T. And remember, this implied, this was our lemma, that x must lie in T, in fact. Right, this generic vector y, this had this property that it lies in T, but anything that commutes with y lies in T. That's exactly the property that we proved, which made it so useful. I want to prove x lies in T, certainly commutes with y. In general, if I take a vector y in T, there are lots of other vectors commute with it besides the maximal torus. But if I choose a generic in this sense, then as long as it commutes with y, it already lies in T. So that's a property we have here, right? So this implies that x lies in T, and this implies that this Lie algebra is equal to T. So then they have the same identity component, and by compactness has only finite components, and that's the Weyl group. So it's finite, and now I want to see how it acts. That it acts on the Lie algebra, or on T. So I claim W acts on the maximum B and subalgebra T. Well, how should it act? W is a normalizer. Something in W is a normalizer of T. Right, so that means that I can represent W as adjoint of something. And such that T is contained in T. So therefore, adjoint, if I take the adjoint, it takes a Lie algebra into the Lie algebra. So that's how W acts. Of course, W is not unique, right? So G is unique mod the maximal torus. Right? My Weyl group is this divided by the maximal torus. So if I modify it with anything that's inside the maximal torus, I get the same element of W. So if I write W like this here, I can change G with anything in the maximal torus. But of course, at of the maximal torus, restricted to T, is identity. Of course, T is abelian. And little t was a Lie algebra of that. So it commutes with everything. So the adjoint of that's identity. So it doesn't matter what I modify it with. So as long as I modify it with anything, I get the same thing as an element of as an action on the Lie algebra. So it's actually important to show that the centralizer here is equal to T. I'm using that property now. Right? Okay, so now I have an action. So that's the action here. So I have a finite group acting on my Lie algebra. And now I want to show this last property, important property, that these orbits are the same. So what does that mean? So it means that, so let's take a vector in the intersection. Right? So let's take a vector y in at g x intersected t. So there exists, in other words, there exists a little g. So that at little g of x is equal to y. Right, y is one element here, so write it in that form at little g of something. And what we have to do is I have to show that both x and y lie in t. Right? I started with something in t because I could do that. And y lies in t, so I have two vectors in t. One is an adjoint of something, and I have to show that there exists a w in the while group such that w of x is equal to y. So that means they have the same orbit. So I have to produce something in the normalizer, something that normalizes the maximal torus. And that's a little tricky. It's going to centralize our. Let me just look how it starts. Yes, you look at the centralizer of x. So what does that mean? It means that all elements g and g such that at g of x is equal to x. And that will be the centralizer in the group G if you want to. So what, in general, I would have to specify where I take the centralizer. Right? This is a set of elements that centralize it. So I claim what sits in there. X or Y? Came that this certainly contains the maximal torus, right? Since at G on here is identity. If do we know about G? We know that at Gx is equal to Y. Of course, so this is a set of all element G that has this property So t lies in here. If I choose something, an element in t, so here I put the element in t here, x and y lie in the Lie algebra of the Lie group, so therefore it's identity. So because x and y both lie in t, so if I multiply, if I take adjoint of something in the maximum torus, it's identity. So it contains t. And now I claim it also contains GT, G inverse, the conjugate. That's also in the centralizer of X, where G is my element, so this is my element right here, which I fixed so that at Gx is equal to Y. Right. So maybe this notation is a little bit unfortunate because this element G is fixed, and here take any element in G with this property. Right. Maybe a better notation might be sort of H and G that take X to X, whereas here my G is fixed. Let's call it G naught maybe to make that clearer. So here I take the conjugate with respect to that fixed element of the maximal torus. T is already contained in there. Actually, that's also inside Zx. So let's see, what do I have to show? It should have to show that adjoint of that X trivially on X.
Well, it's a kernel.
Pardon?
It's a kernel. So it is normal. If it contains T,
Yes.
it will also contain its conjugate images.
It's normal inside the normalizer. G naught is some element in G. A priori, I don't know where G naught lies. Why should it normalize the center? Oh, sorry. No. As long as it has this property, it's in the centralizer. The centralizer is not a normal subgroup inside all of G, is it?
Yes, it is defined
By an equation.
as a kernel.
You're right. This is normal in G. And this implies that this is true. So conjugate of the maximal torus. It's also inside the centralizer. So now I have two tori inside the centralizer. So think of this as my new Lie group. So Zx is a Lie group. Forget about where G comes from. It's some Lie group. They'll be connected. Right? But both T and G naught T, G naught inverse are maxima tori in the identity component of the centralizer. Right, the centralizer was a normal subgroup. It's also closed. So in effect a compact Lie group. Has finely many components. Let's look at the identity component. These tori are connected, so this must lie in the identity component. So I have now two maxima tori inside the identity component of a new Lie group. Now I can use the fact that they're conjugate. Right, we said in any Lie group, if I have two maxima tori, they conjugate by something inside the Lie group. So it means there exists something in this Lie group, in this Lie group right here, such that H takes T into this other maximal torus. So what does that mean? So I can now bring G naught on the other side. So it means G naught H T times H inverse or H G0 inverse is T H inverse G0. So that's, of course, the inverse of this. So I can think of this as, say, what should I call it? X, T X inverse, where X is equal to G0 inverse H. inverse of that is H inverse G0. Right? So this element is something that takes T to T. Right? So X T, X inverse is equal to T. That by definition means that X lies in the normalizer of T, little x. And what does little x do?
It also takes x to y because she did and the h is 3 then.
Right, so I want to claim that at x, bad notation, x is equal to y, because x was G0 inverse h. So this is at G0 inverse h of x, which is...
In fact, we should take it the inverse.
Yes. I want to put the G0 on the right-hand side. So let's define x as the inverse of that. So now it means this. That doesn't matter. It still means that x lies in the normalizer. So I can let this to be h inverse G0. G0 x trivially, so that's at h inverse times x. At G0 inverse was x, yes, okay. At G applied to x is equal to y. So and that's at x, so I have so I can put this on the other side. So I get at of h x is equal to y. X was in the normalizer of the torus, and h was in the centralizer of x. That means x trivially on x.
Hx is G0 nu.
Yes. G0 inverse h. Did I want it on the other side after all? I want to claim that hx lies in the normalizer of t. So this here says that h is what? H inverse. Put it on the left-hand side. So it's G0 inverse times x inverse. Oh, God. G0 times x inverse. That's h inverse being on the other side. That's an h. That's G0 multiplied by x inverse. So h is G0 x inverse. Maybe here. That's how I continue here. Making it too complicated. What's at h inverse y? I claim that's X is my element to normalize, right? That's my element that I want to choose in the while loop. So I would like to show that add X takes X to Y. So maybe I should have done the other way around after all. Right, I want to use the fact that add H lies in the centralizer. Right? This was in the centralizer. It's actually on X. So I would have liked to have it the other way around. So let's X to be this after all. So then at then add X applied to X is at of G0 X inverse applied to X, H inverse, sorry. H.
G0 inverse H.
J0 inverse H. H lies in the centralizer, so it's at of G0 inverse applied to X. But at G0 inverse applied to X is I want Y. There's clearly some order. You have to do it in the right order. I do it like this. It's another way of saying that, right? So I could also say G0 inverse T, G0 lies in a normalizer. So then, what lies in the centralizer, bring G on the right, so then G0H centralizes T, takes T to T. So G0H lies in the normalizer of T inside G. How do we write like this, right? So now I take at G0H. Let's see if that works. What's at G0H applied to X? Well, H lies in the centralizer, so that's at G0 of X. What's about at G0X? That's Y. Okay. So the trick was to put the inverse on this side. Okay. Okay. So we found something which takes X to Y, which also lies on normalizer. That's my W now. So W is equal to, what was it, G0H. Okay. So that proves that. So that's the one of the important properties of the Weil group. When I'm restricted to the maximal B in subalgebra, that's where the adjoint orbit intersects. I need to do examples. Let me just maybe quickly finish one example, an easy one. Let G be the unitary group. What should be the maximal torus be? Well, what's your guess for the maximal torus unitary group? Something that's abelian. So diagonal matrices, right? So e to the I theta 1, e to the I theta n. So it's abelian, right? Clearly it's abelian. Why is it maximal abelian? So let's say I have a matrix A which commutes with T. So commutes with every element like that, right? What does that mean? Well, I can think of these, say, choose a theta I all distinct, then the coordinates are the eigenspaces with this eigenvalue. If something commutes with A, that means A must preserve the eigenspaces. So preserve each coordinate, that means it's diagonal. So it's clearly a maximal torus. What is W? This normalizes the maximal torus. Instead of commuting with it, normalizes with it. What does that mean? So if a matrix normalizes another matrix as opposed to commuting with it, what can it still do? It doesn't quite have to preserve eigenspaces, the individual eigenspaces. It can permute them. So there's no reason, if it doesn't commute with it, there's no reason that if I apply it, say, to this eigenvector, I get the same eigenvalue. But I get some other eigenvalues possibly. So all it can do is permute. So W permutes the coordinates in the Lie algebra. Lie algebra I can view as a set of all I theta 1 up to I theta n. That's the Lie algebra of this maximal torus here. So the while group are the permutations or the theta i's. So W is just a permutation group on n letters. Okay. Look at the adjoint orbit. So now I can understand the adjoint orbit inside the unitary groups, what they all look like. Of some vector x in the Lie algebra. So x has this form, I theta 1 up to I theta n. First I claim, so remember I said the adjoint orbit intersects it in the Weyl group orbit. So if I have an element like this, now look at its adjoint orbit, in other words, I'll matrix conjugate to this, that's what it means, right? Then I can change the order of the theta i's. Right? So that means their O intersected T has a unique element where I'll say order the theta i's in size. Right? So I can permute, I can make it into this order. That's unique, of course, then, modular permutation. So now how big is it? So if I take such an orbit to such an x, it's equal to G mod the isotropy, but the isotropy is a centralizer. Everything commutes with x. So what are the matrices that commutes with x here? That depends how many are equal. If they're all distinct, then only the maximal torus commutes with it. Right? So if theta 1 less than theta n, then the adjoint orbit is just G mod the maximal torus. Right? But the same argument is over there. That's the only thing that commutes with it, if they're all distinct. Right? I'm fixing a vector now. This is a fixed vector. I want to see what everything that commutes with it with this fixed vector. If we're all making all distinct, it's just the maximal torus. So G mod the maximal torus is the most basic adjoint orbit of a Lie group. If it's not, say what happens when theta 1 is equal to theta 2, say equal to theta k, but the other ones. So what happens, say, if some are equal? Let's say the first two are equal. What's the normalizer then? And say all the other ones are distinct, for example, if you want to. So then think of the first two elements. So then I have, say, 0 I theta, 0, 0 I theta. This will be the first block. What commutes with this? Even much more. This is a multi-identity. Everything commutes with it, meaning the whole block. Right? So when you have equal eigenvalues, you get a huge block, which lies in the centralizer. So in other words, what these things all look like depends on how many eigenvalues are equal. So the first n1 eigenvalues are equal, but distinct from the next n2 eigenvalues, which are equal. So this gets in blocks, has a kind of block form. So the hadron orbit is un mod un1 un, say L, and of course the summation ni must be equal to n, must add up to the whole matrix. So all these are precisely the hadron orbit inside the unitary group, inside the Liada unitary group. So these are very nice. They're also called flag manifolds, very basic, important objects. For the other Lie groups, things are a little bit more delicate. But this is the one that's easy to understand, and that's kind of the basic example. Okay, maybe I should finish now. I'll talk about, say, the other examples a little bit on Monday, and then I start with the next chapter. You'll notice that we are